Hello, and welcome back to the course on thermodynamics. We are now on the last lesson for Unit 3 of this course. So let us first recall what we have discussed so far. So we have discussed about the adiabatic process in the previous lesson, wherein there is no heat involved in this type of process. So meaning the change in internal energy of the system is just equal to the negative work done by the system. We also discussed the ratio of the heat capacities at constant volume and at constant pressure in the previous lesson, and they are all related by the gas constant R. So in this lesson, we will be trying to we will discuss, or we will focus our discussion on the thermodynamic process called the adiabatic process. So we will discuss adiabatic expansion and adiabatic compression in detail. So since this is the most general kind of thermodynamic process wherein the pressure, volume, and temperature doesn't necessarily change. So what is the relationship between the temperature and volume in adiabatic processes for an ideal gas? So this is an adiabatic process for an ideal gas from state A to state B. So you will notice the pressure changes. So in this case, it's an adiabatic expansion. So the volume increases from VA to VB, the pressure decreases from PA to PB, and the temperature increases from point A to point B. So the temperature at point A is greater than the temperature at point B. So since there are two isotherms here, isotherm for A, this blue curve here, and the isotherm for B, this curve here. Okay. So it's decreasing temperature, increasing volume, decreasing pressure. So the relationship between the two from from derivation from the ideal gas law is this one. So the temperature times the volume raised to the gamma minus 1 is constant. So this means that T1 V1 to the gamma minus 1 is equal to T2 V2 gamma minus 2, or Ti Vi is to the gamma minus 1 is equal to Tf Vf to the gamma minus 1. Take note that if this is not an adiabatic process, the relationship between temperature and volume of an ideal gas is actually V over T, if it's a constant pressure process. If you will recall Charles' law, it's actually T1 V1 over T2 V2. But this is only true for constant pressure. But since in an adiabatic process, the pressure is no longer constant, then the relationship between the temperature and volume of the ideal gas is now given by this. So it now depends on the factor called gamma, the ratio of heat capacities. So the temperature is actually inversely proportional to the volume. So an adiabatic expansion means a decrease in temperature. So you expand the volume, you increase the volume, you decrease the temperature. So since gamma is always greater than 1, therefore the power of Vi here is always positive. Gamma minus 1 is always positive. So meaning the relationship between Ti and Vi is inversely proportional. So how about the relationship between pressure and volume? So pressure and volume is related by this one. So if you will notice, if the pressure decreases, the temperature also decreases. Sorry, volume. If the pressure decreases, the volume increases. So the relationship between pressure and volume is also inversely proportional. So in adiabatic expansion, the volume increases, but the pressure decreases. Okay. So how do we calculate now the work in adiabatic processes for ideal gas? So since the work is just equal to the negative change in internal energy, so work is just equal to the negative change in internal energy. And since the internal energy is NCV delta T, and the negative of that is NCV Instead of Tf minus Ti, the positive change, you have Ti minus Tf, the negative change, because that's negative change in internal energy, therefore negative change in temperature. So it's also equivalent to this 1 over gamma minus 1 PIVI minus PFVF, or P1V1 minus P2V2. So that is how you calculate the work in an adiabatic process. So take note that the work depends on the negative change in temperature. Meaning, if you have a positive change in temperature, increase in temperature, then the work is negative. So the work, and in this case, the work is done on the gas, on the ideal gas. If the change in temperature is negative, or you have a decreasing temperature, then the work done is positive. Work done by the gas is positive. So the gas is actually the one doing the work. So this is a sample image of adiabatic expansion. So the gas expands, and when the gas expands, the temperature decreases and the pressure decreases. And an adiabatic compression, on the other hand, uh, the volume decreases since it's a compression, but the pressure increases. So the reverse of this path here from B to A is an adiabatic compression. So the volume decreases, but the pressure increases, and the temperature also increases. So in the case of adiabatic expansion, the work done is positive because the gas is the one doing the work. In adiabatic compression, the work done is negative because the gas is not the one doing the work, but its surroundings. In this case, in this picture, the piston is the one uh, doing the work. So let's have an example. So this is adiabatic compression in a diesel engine. So you have a diesel engine. We will discuss more about engines on the next units. The compression ratio of diesel engine is 15:1, meaning the air or the gas inside the cylinder or the piston is compressed to 1 over 15 of its original volume. So if the initial pressure is 1 atm and the initial temperature is 27 degrees Celsius, find the final temperature and pressure after the compression. That's for the first question, letter A. For letter B, how much work does the gas do during the compression if the initial volume of the cylinder is 1 liter? And assume the air is a diatomic gas. So we actually have a similar problem like this before when we discussed about uh, the previous lessons. So for letter A, so this is the relationship now between temperature and volume in an ideal gas. We are asked to find the final temperature. We are given the initial temperature, 27 degrees Celsius. You need to convert that into Kelvin by adding plus 273, so that's around 300 Kelvin. We don't know the initial and final volumes, but we know the compression ratio, the ratio between V2 and V1. It's actually 1 over 15. So solve for T final here. So divide both sides by V final to the gamma minus 1, and you have this. So Vi over V final, this is just the compression ratio. This is V1 over V2. And V1 over V2 is just 1 over 15, the compression ratio. So if V final, or sorry, uh, if say, the initial volume is 15 liters, then the final volume is just 1 liter. So meaning the ratio always of uh, V final or V initial over V final is 15. So the compression ratio V final over Vi is 1 over 15, but Vi over V final is 15. So V initial, the initial volume is always 15 times the final volume. So the final volume is always 1 over 15 of the initial volume. So this ratio here is equal to 15 over 1 or 50. So since for an ideal gas, CV is 5 subs R, uh, so we still need to solve for gamma, and we are only given that it's a diatomic gas. So for a diatomic gas, sorry. So for a diatomic gas, its CV is 5 halves R, that's 20.79 or 20.8 joules per mole Kelvin. So its gamma is actually 1.4. So you can actually use gamma 1.4 if it's a diatomic gas. You can use a gamma 1.7 if it's a monoatomic gas. So you can do away with this derivation here and automatically use 1.40 if it's a diatomic gas. Because if for a ideal diatomic gas, the gamma is 1.40. So gamma is 1.40 minus 1. You have this. Again, you convert 27 degrees Celsius to Kelvin. It's around 300 Kelvin. And you will get a value of 886 Kelvin, or if you convert it back to degrees Celsius, it's 613 degrees Celsius. Okay, so we now know the temperature. So we are asked for the final temperature and pressure after the compression. So let's now solve for the pressure. So we use this relationship again between the pressure and volume during an adiabatic process. So solve for the final pressure. It's just this one. We already know gamma is 1.40. So it's 44.3 atm or 44.8 times 10 to the 5 pascals, depending on what is required of you by the problem. So for letter B, how much work? So there are two formulas for work actually, but we'll just use this one. So 1 over gamma minus 1, P1 V1 minus P2 V2, or P initial V initial minus P final V final. So you substitute all of the values, but make sure it is in SI unit. The pressure must be in Pascal, and the volume must be in cubic meters. So the volume that we used here, the initial volume is 1 liters. So 1 liter, if you convert that into meter cube, you multiply by 10 to the negative 2. So this is 1 liter. 1 times 10 to negative 3 meter cubes or cubic meters. So the final volume is 1 over 15 of the original volume. So if the initial volume is 1 liter, the final volume is 1 over 15. Again, to convert that into cubic meters, you need to multiply by 10 to the negative 3. And of course, all of the units will correspond to the unit called joules. And you will get a negative value for work, which means work is done on the gas, because this is a compression. So compression means the outside, the surroundings of the gas is the one doing the work. So it's not the gas that is doing the work. So the gas is being compressed by its surroundings. And in this case, the piston is the one compressing the gas. Hence, you get a negative sign for work. Okay, another example. This is adiabatic expansion of argon gas. So during an adiabatic expansion, the temperature of 0.450 moles of argon gas drops from 50 degrees Celsius to 10 degrees Celsius. So this is a negative change in temperature. So the argon will be treated as an ideal gas. So draw a PV diagram for this process. How much work does the gas do? And what's the change in internal energy of the gas? So first, draw a PV diagram. So this is an adiabatic expansion. So meaning you have two isotherms here. This is the 50 degrees Celsius isotherm. You can convert this to Kelvin. And this is the 10 degrees Celsius isotherm. So state 1 is 50 degrees Celsius, and it has a higher pressure as compared to state 2, which has a lower pressure. State 1 has a lower volume as compared to state 2, which has a higher volume. So this is the PV diagram for this case. So there's a decrease in temperature. So second question, how much work does the gas do? So work is just NCV delta T. So the work done by the gas is just the negative change in internal energy of the gas. So you have negative NCV delta T, or NCV times negative delta T. So we have this one, the work done by the gas is positive 224.5 joules. So this is expansion. So we expect the work done to be positive. So there's an 10 minus 50 is negative, but there's a negative sign here. That's why it becomes positive. So of course, the change in internal energy with the gas is just the negative of the work for an adiabatic process. So in this case, it's negative 224.5 joules, the negative of this one. So we expect a negative change in internal energy, or a decrease. A negative change means a decrease in internal energy, because we have a decrease in temperature from 50 degrees Celsius to 10 degrees Celsius. So that one. So the temperature of the gas decreases, meaning the internal energy of the gas also decreases. And that is it for the last lesson of Unit 3. So that completes Unit 3, the unit on the first law of thermodynamics. So for the last unit, we will just continue to the second law of thermodynamics. And you will be talking there mostly about uh, heat engines and refrigerators. So I will see you again in the next lesson.